Going to continue with Euler tours today. I'm going to prove that Fleury's algorithm actually produces an Euler tour, and then give one really cool application of Euler tours as well. Okay, so let's just remember Fleury's algorithm maybe in a kind of informal way. So this was a way of producing an Euler tour, and the way that it worked is very simple. We start at a vertex, and we just walk along edges, taking care, and remove edges as you walk along them, always taking care to avoid crossing a bridge if you can, right? So if walking along that edge disconnects the graph, don't do it if you have other options. If it does disconnect the graph, then walk along the edge. I mean, you have no choice, and potentially remove a vertex as soon as it becomes isolated. Okay, that's sort of the rule. So start at an arbitrary vertex and walk along non-bridges when possible. Remove traversed edges. So once we walk along an edge, we remove it, and remove isolated vertices. So if at some point we create a vertex that's isolated, then it gets removed. And this is going to allow us to remain connected, this property here, because it's going to turn out that when we're forced to cross a bridge, the only time that happens is when it's connected to a single vertex. So we'll never have a situation where we had two bridges to walk across. Okay, that'll be an important part of the proof here. Okay, and so the theorem is that Fleury's algorithm produces an Euler tour, if there is one to begin with in the graph. Okay, if there's not an Euler tour, I'm not going to put that as part of the theorem here, but we'll see that the thing breaks down. I mean, if there isn't an Euler tour, you can't produce one, so something will go wrong with this algorithm. It won't do what it won't end up like. How do we know it's completed? Well, if at the end all edges have been removed and we're where we started, then it would have been an Euler tour. Okay. All right. So what's the proof? Let's suppose that we're running the algorithm and we're at some arbitrary step, and the current vertex is u. Okay, so let's initialize a few things. So let v be the starting vertex. Okay, so we started at vertex v, and we've gone on. I mean, we've taken a few steps in the algorithm. Let u be current vertex. Okay, and let h be graph of, let's say, the remaining graph. So at the step we're at. So h is whatever is left after performing the steps that arrived us at u, right? So we removed some edges potentially, and potentially some vertices if they became isolated. The sun is amazing. It's like shining through like 4 different trees, and it probably will only be on my face for another minute here, but okay. Okay, so first I want to make a little observation here that at this moment here, so first of all, so the graph that we're starting with was connected, and all degrees were even, right? To have a chance of having an Euler tour, those two things had to be true. And in fact, if you wanted to actually implement this algorithm, that's what I would actually say to do, is don't run it on a graph you don't know whether or not it has an Euler tour. Do the easy check whether or not it has an Euler tour by checking all degrees. If they're all even, then run the algorithm and actually find one, right? That'd be one way of doing it. You can actually skip that part if you want, but then our proof doesn't actually work, and you have to prove it somehow else, right? So you can add that to the algorithm if you want, but let's just assume that our graph does have an Euler tour. In other words, all degrees are even. So all degrees are even, and when you perform this procedure in Fleury's algorithm, right, how does it look, right? You start at a vertex, then you walk somewhere, and then you walk out, and then you walk out, and you walk out, and you walk out. Say we're here at this point. Maybe you can even revisit vertices. So say we're here. Okay, so these edges have all been removed, and the remaining graph is like, something here. I mean, it could include these vertices too. Maybe that's not all their edges. But the point is, in H, there's only a couple of vertices that are candidates for being of odd degree, right? The only vertices that can be actually, so I can write, this is kind of like the complement of H, right? The edges that are actually drawn, those get removed. Odd are, which vertices are candidates for having odd degree? So yeah, sorry, that can be odd degree. So we're running this algorithm, and we started at this vertex V, and we're currently at vertex U. Those are the only two vertices that could be of odd degree. Any other vertex was visited and then left. And so its degree started even and dropped by 2. Drop by 2, drop by 2, drop by 2. This dropped by 2 twice, so its degree is still even, right? So V and U are the only vertices that could even be odd. And actually, they might even be even. What's the one situation where U and V actually remain even? It doesn't seem possible, but there's one sort of, it's not degenerate, but one scenario here where U and V are actually even. So U and V are the only ones that could be even, could be odd, and actually they might even be even if U equals V, right? The starting vertex is V, and the current vertex could also be V, right? We could be at the first step of our algorithm where we haven't done anything yet, or at some point in the algorithm, we could have returned to V and we still have more steps to make, but at that moment in time, the degree of that vertex is even, okay? That's not important that it's even. The point is there's only two vertices that could ever be odd. That's going to lead to our contradiction later. We're going to find an odd degree vertex that's neither U nor V, and that's a contradiction, okay? So it's not important that U and V are odd. It's just important that they're the only possible vertices that can be odd in H at this point, okay? And still even if U equals V. It's not important, but it's just to be clear there. In the notes, I've written it as a separate case, but if you phrase it this way, it's just one case you can deal with. Okay, so what we'd like to show, and this will prove our theorem, although I'll still state it here. So we want to show that H is always, so I'll just say H is connected. Okay, but as this algorithm runs, H gets updated, right? H is like an edge gets removed, an edge gets removed, an edge gets removed. Potentially a vertex gets removed if it becomes isolated. And I would claim that H is connected at every single step. And we'll see, just with a little bit of thought, you may see it already, that this implies that the tour that we take, the walk that we take, will eventually return where we started and use up all the edges. That follows from the fact that it's connected and from the fact that the degrees are even, okay? So those two facts prove it. Well, I'll restate that at the end once we've established this fact though, okay? So I want to show that. Okay, so we're in the algorithm here and we're currently at vertex U, and let's say that the algorithm tells us to traverse to vertex W, okay? So that's the edge we're gonna walk along, okay? When I have choices, the algorithm doesn't specify, so I'll address a couple of cases, what this edge UW looks like. Okay, so suppose next edge to traverse is UW. Okay, so that's like the next one there. So what happens, I traverse UW and I remove it. Okay, and so there's a couple, okay, there's actually one question actually to consider. Is there even such an edge? Is there a W to traverse? I mean, maybe I, like we go up here, maybe I walk around and I end up in U here and there's nothing to do. Right? Maybe the algorithm's stuck, right? I do have to address the possibility that I don't have, that it's halted at this point. But how do I know the algorithm can continue even when I've reached U there? So basically there's two things. I mean, either since U is odd when it's not equal to V, there's an edge coming out of here, right? I mean, at this point, there's an odd number of visits to you, not an odd number of visits to you, but an odd number of U's edges have been used, and I'm there. But because degrees are even, there's always a way out. So there's definitely an edge incident to U, which means I can always walk out of it, right? So yes, as degrees even and U degree is odd, right? The degrees are even in the original graph and the degree of U is odd in H. There's one other scenario, and actually that is a scenario where we can't walk. That would be if U equaled V and there's no edge to take out of there, then there's no step to do. But H I mean, H was connected and there's no step to take, so it remains connected, right? The algorithm would terminate. I haven't said that like we emptied H. It's just there's always there is an edge to walk along unless we're basically done. Otherwise we're closed. Okay, we'll address that in a moment though. All right. So there is an edge to walk out of in virtually every single time, unless basically you're done. Okay, so let's look at what are the possibilities for that edge. So the first one is if UW is not a bridge in H, right? When we talk about walking along bridge or non-bridge edges, we're always talking in the remaining graph H, right? An edge may not be a bridge initially, but it may become a bridge, okay? So if we walk along a non-bridge, what do? We remove that edge. So what can you tell me about this graph? H minus UW, which is my new H. It's my updated H. This graph will be I want it to be connected, and is it connected? Yeah, I walked along a non-bridge. You can remove non-bridges safely. Bridges are the things that you can't remove. So bridge H minus UW is still connected. Okay, so that case is not too interesting. That one's easy. Okay, so otherwise, yeah, so that means that UW is a bridge. Okay, suppose UW is the only bridge at U. Okay, so if UW is the only bridge at U, then it actually means it's the only edge at U, because I'm at U and I always walk along an edge that's a non-bridge if it's available. There are no bridges, there are no non-bridges, otherwise I wouldn't be walking along a bridge. And I'm supposing that there's just a single bridge there, so it literally means there's a single edge, right? Just UW is the only edge, okay? So what happens here when I run the algorithm, I walk along edge UW and delete edge UW. What else will I delete in this step here? Right, so my picture looks like this. Here's U, here's W. This is actually a bridge, so there's further stuff there. Is there anything incident to U? Other than that, no, because like this, I've just said this is the only bridge here. So what does the algorithm do? It walks along the edge and deletes it, and it also deletes vertex U, because in this step, U will become isolated. So the new H is actually this graph here. We remove the edge and the isolated vertex there. And this thing's still connected. It wouldn't be connected if I didn't remove U, because then I'd have a component with U by itself, but carefully, the algorithm also deletes the vertex U, okay? So that's connected. But the real case we have to address is, what if the picture looks like this, and we're at U, and there's a bridge W here and a bridge W prime here? That's not a very pretty W there. Okay. If I have this situation here, then at U, I walk along one of these bridges, and that disconnects the graph, but I'm not allowed to delete U, because U is not an isolated vertex. So if I have this scenario, I don't know what to do. So I want to prove this can't happen, right? Because otherwise, like, this causes a problem. This will disconnect my graph here, okay? So suppose there are bridges UW and UW prime, okay? And so my algorithm, I'm at U and it says, okay, walk along a non-bridge. Well, there's no non-bridges. Okay, walk along a bridge. I have two choices. Okay, this is bad, because this is going to disconnect my graph. So let's find a contradiction here, hopefully, so that we never arrive in this situation. That would be ideal. Okay. Okay, so the picture looks like this. We're at U, there's two bridges. There may be additional bridges too, but two is enough to cause the contradiction here. Okay. Now delete or remove edges UW and UW prime. So remove both these bridges from H. Okay, so this produces an H minus UW minus UW prime. The algorithm doesn't do this. I'm just saying, consider this graph here. Okay, like remove the two edges and think about this graph here. Okay, and now let W, big W and big W prime be components that contain W and W prime respectively. Okay. So again, we're not talking about the algorithm anymore. We're just talking about this graph H. Okay. So let me draw a picture again here. So here's U, here's W, and here's W prime. I'm going to remove these two edges here. Both of them are bridges, and so I know what happens, for instance, is that I'm left with a component here that contains W and a component here that contains W prime. And then actually there's there's still a component here, U, that contains U and whatever else U is adjoined to. So in this case, when I remove two edges, I actually get three components, but I remove two edges. And I don't remove the end vertices. It's possible that W and W prime are single vertices by themselves, right? That's a possibility. Okay. All right, so now, what do we know here? Well, we know, so what should I say here? Okay, so V, that was my starting vertex. So starting vertex, vertex V. I have no idea where it is in this picture. I haven't labeled it. But one thing it's not in, that's big W and that's little w, or W prime. It's not in W and W prime simultaneously. I mean, those are two disjoint sets of vertices, right? So is not in W and W prime. It may not, it could be in neither of them, but the point here is that without loss of generality, we can say that V is not in, say, W, right? It's not in both, so one of them it's not in. It's either not in W or not in W prime. Let's just say it's not in W. It's symmetric, okay? Okay, oops. What else do we know? U is also not in W, right? U is over here. It's clearly not in W just simply by construction. So these two vertices are not in W. Okay, but little w, which is in big W, has, what can you tell me about the degree of this W after removing this edge here? So before removing this edge, what was the degree of W there? Like just, we've run the algorithm, we're sitting at U, which is the next, which is our pending vertex. Every other vertex in the graph that's not V or U is even. Yeah, exactly, Eric. So it has even. Oh, okay, so it had even degree originally, but after removing this one edge here, it now has odd degree. So it has odd degree. Oops. And just to emphasize, in this graph, H minus UW minus UW prime, right? This one, these red edges removed. W has odd degree, okay? Now, big W is a component. So big W itself is a graph, right? Like if you just focus on W as itself, it's a subgraph of the graph, like all the edges in there. If I have an odd degree vertex in this W here, what does that imply? Is it possible to have a single odd degree vertex in this component? No, no way, right? Handshaking lemma says no. It says there's got to be another vertex inside of W of odd degree. Okay, so by handshaking lemma, there exists, say, an X in W with, well, X is different than W, little w, of odd degree. Okay, so there's some X in here. All right, now X, yeah, Eric sees it, right? What's up with X in H? In H, I haven't done anything to X. X is the same as it was in H, right? Its degree is unchanged. So it should have been even, unless it possibly was U or V, which were the odd candidate vertices, but they're not in there. So X is a new odd degree vertex in H that didn't exist in the first place, right? But that is an odd degree vertex in H that's distinct from U and V, which were the only candidates for odd degree vertices. W was not a contradiction because W had even degree in H, and then I artificially removed this edge. But artificially removing this edge gave rise to the existence of an X, which was impossible, okay? So why was this not a contradiction in the previous case? If I only had one bridge and I removed it and tried to do the same argument here, it's possible that X was V, right? That could have happened. But what in this case, V couldn't be here and here simultaneously. If V was in here, then I can make the same argument on W prime to get the contradiction. So this contradicts the existence of two bridges, okay? I think that's a great argument, right? That's really like cool. These are really fun ones when you show the existence of an odd degree vertex by using the handshaking lemma. It's always nice to see that. Okay, so this means that H remains connected, right? We proved our assertion up here that we wanted to show that H was connected. So H remains connected throughout this procedure. And now let's convince ourselves real quick that this actually gives the thing. Okay, so H remains connected, and H is the remaining edges to traverse. Oh, sorry, I haven't been checking the chat here, but Eric says he should turn his camera off. No, please don't. It's very good to get feedback. So, so H remains connected, and then and I don't know why I have this. And as degrees are even initially, so that's we started with all the degrees even, we can always leave a vertex we visited, right? So we started a thing we can always walk, right? You can always continue walking because of even degreeness, and you never become disconnected. So if you just think about it for a second, what does this mean? It means if you start in V and you just start walking and you never disconnect the graph, you have no choice but to eventually eat up every single edge and come back to where you started. There's no alternate way. I'm going to just leave it at that. If you're not quite convinced, try for a contradiction. Imagine that this procedure left something that over, then it implied that the thing was disconnected because it meant there were some edges out here that were not traversed, but I had to end up in V somehow because the degrees are even. Like you eventually stop in V no matter what, right? Just think about it. At every point it's even, so you can always walk. The only way to, like, this will have an edge that's never traversed unless I actually get there. So I have no choice but to get back there. And if there were edges untraversed, it meant that the thing was disconnected, okay? So this gives an Euler tour, okay? It's not that hard of a proof. There's just that cool contradiction here that there's never two bridges, okay? So what it says is, indeed, the algorithm is well phrased. Walk along non-bridges as long as you can. If you have to take a bridge, there'll only ever be one bridge, okay? And I think when we ran this algorithm in the first class, we actually saw that as well, that we created some bridges in the graph, but anytime we were at a pending vertex and there was a bridge, it was always the only choice we had to make. So, okay, good. So Fleury's very simple algorithm works. Now I want to give like a really cool application here of Euler tours here, like a way to construct something that doesn't seem to have anything to do with them on the face of it. Okay, so let's produce something here called a De Bruijn sequence. So a De Bruijn sequence. I'm going to denote these DBS of order n. This is a definition. Is a cyclic. I'll explain exactly what I mean by this once I finish defining the rest of it. Binary string. string. Okay, so you've got this 0, 1 string that contains every length n binary string as a contiguous substring. Okay. All right. So let me explain here, and I'll give a couple examples to make this very clear here. So if I'm looking for a De Bruijn sequence of order n, it's a big long 0, 1 string, a huge 0, 1 string that contains every length n binary string. So if n equals 2, the length n binary strings that it needs to contain are 0, 0, 0, 1, 1, 0, and 1, 1, right? Those are all length 2 binary strings. And I need to come up with a longer binary string, necessarily longer, that has all of these as substrings and a few key points. Contiguous means they're a substring and they're in a row together. You can't like skip things, okay? There are definitions of substring where you can just look for a sub pattern and drop out things. They need to actually appear in a row. So I need to see somewhere 0, 0, then 0, 1, then 1, 0, then 1, 1. Those necessarily need to appear. And what's the cyclic business mean? that means that when I look at trying to find them contiguously, I can go off the end and then begin at the start. I'm allowed to look for strings that way too. Like I can go from end to start. So you can imagine the string being drawn in a circle, and I want to find them there. Okay. So let me draw a couple examples. What would be maybe the most naive way to actually produce a de Bruijn sequence here of order n for n equals 2? Like, say I wanted all those guys to appear. What's the dumbest solution here? Or like the easiest where you don't have to think? Okay, so Van's already, yeah, Van has that's not the dumbest answer, Van. Shame on you. So, no, it's okay, yeah, there we go. So just like list all 4 of them in a row. Like not very efficient, but at least we'll definitely get them all. So, so just as an example, but this one's not very good. 0, 0, 0, 1, 1, 0, 1, 1. Great, they're all there. There's the first 2 bits, then this one, then this one, then this one. But as Van pointed out, there's definitely a better solution. And this immediately begs the question, okay, great. I can definitely create them by just stringing all of them together, gluing them together. But like, I'd like to do it efficiently. How can I get them all to appear in a very short amount of time? Okay. So this is a long, let's say, de Bruijn sequence. It's not a very good one. Like, let's find a smaller one. And I think Van's suggestion here should work. 0, 0, 1, 1 is actually only length 4. And let's just double check. It's got 0, 0. It appears right here, right? It's got 1, 1. That appears right here. It's got 0, 1. That appears right here. And then the last and interesting one, where's 1, 0? Yeah, it wraps around, right? We said that this cyclic business is important. That's 1 to 0 there. They're contiguous in that way. If you draw it in a circle, and actually in applications, this is kind of like, this is relevant that it's drawn here, and so I want them all to appear. So this was good. This was length. This was a good one, right? This was length 4, which was good. Okay. All right. So yeah. So that's one example, and then I think let's look at n equals 3 real quick, and let me draw one that's not, and then one that is. So say we have something like 0, 0, 1, 1, 0, 1. Why is this not a DBS? So this is not DBS of order 3. Yeah, exactly. Eric says there's no 0, 0, 0 here, right? And just to reemphasize, 0, 0, 0 does appear as a substring by the strictest definition, right? We have, like, it's literally there, just drop the ones, but we want them to be contiguous, right? So we want them to actually appear there. Otherwise, the question's not as interesting. Okay, so yeah, is missing, for example, 0, 0, 0, okay? But maybe we have this one, I think this has them all, 0, 0, 0, 1, 0, 1, 1, 1, okay? This is. So, I mean, there's 8 things to check. I'll maybe not go and check all of them, but you have to actually check if they're all there. 0, 0, 0, and 1, 1, 1 are certainly there, but there's a handful of others that need to be checked, okay? So that's the claim here. All right, so what's the length of this one that I produced here? Yeah, Van's suggesting maybe the length should be 2 to the n here. That's what the theorem's going to be. Let's at least show that 2 to the n is a reasonable thing to even start with. Like, we can't do better than 2 to the n. Okay, so let's make this observation. I'll pose it as a question. How many different contiguous substrings of a fixed length? So fixed is n, but it could be any value here. Are there in a string of length, say, let's use a different variable, x. Okay, so I've got some long string, whose length is x here. How many different continuous substrings of a fixed length, say length 3 or 2 or 5, actually the length doesn't matter, can appear in this? Like, how many different strings even could be substrings here of a fixed length? It's easier than it seems, right? How many different ones are possible here? A contiguous substring can be defined by one bit. Yeah, exactly. One for each element. Because think of a contiguous substring. It has a starting bit and then continues, say length 4. Starts there and goes those 4. The next one starts there and goes those 4. Here's another one that goes 1, 2, 3, 4. Right? It's always 4 bits in a row, and they're just simply defined by, say, their leftmost bit. It's a little confusing in a cycle, but or their starting bit. Right? Those produce different ones. And okay, I could get repeats here, but I certainly don't have more than X of them, right? The most, so there are at most X of them, right? There are most X substrings of a fixed length, and again, contiguous, right? Otherwise, it's just the number of ways of choosing uh, this value, this fixed length. Okay, so that gives me the following lower bound, right? How many 0, 1 strings are there of length n? There are 2 to the n, 0, or let's call them binary strings of length n. So the minimum size de Bruijn sequence of order n. So we use the term order for the de Bruijn sequence because that's not the length; it's just the value. So the minimum size is, and this word size is not right. Length dbs of order n is at least 2 to the n, right? We need at least 2 to the n starting points in order to have any chance of observing all 2 to the n binary strings. Okay. That doesn't mean that we can do it with 2 to the n. I mean, yes, we had examples here. This was length 8 and had all 8 of them. And the 4 example for n equals 2 was length 4 and had all 4 of them. But in general, maybe it's much longer, right? Maybe it's much longer. The theorem is no. There exist de Bruijn sequences of length exactly 2 to the n. And the theorem I'm going to prove here will also actually produce one for us. Okay. Yeah, we should be okay. Okay. So there exist de Bruijn sequences of order n of length 2 to the n, which is the shortest they could possibly be by the above observation. There's no way to have a shorter one than that. Okay. So the way we're going to do this is we're going to construct a digraph, and then we're going to find an Euler tour in the digraph. Now, we haven't actually talked about Euler tours in digraphs. I will mention an important theorem, although this will be an exercise in homework soon. But tours or walks in digraphs are perfectly well defined. You just have to travel along the arcs in the appropriate direction. And an Euler tour then in a directed graph would say, oh, you start somewhere, you walk along arcs in the orientation that you're allowed. You eat up every arc, right? You use each arc exactly once, and you end where you started, okay? And the condition for whether or not you have one, I'll state it in a moment when we get there, but in the interim, you can think about it. Although it's hard to think about it and pay attention, but anyway. Okay, so let's actually construct one here. Okay, so construct a digraph D whose vertex set is all binary strings of length n minus 1. Okay, this seems strange. This does not seem like the obvious thing. You'd think you'd make all the binary strings of length n, because those are all we're trying to find, but somehow we use length n minus 1 here to produce this here, okay? But anyway, it's not clear what the connection is between this and the de Bruijn sequence yet anyway, but that's how it starts. And UV forms an arc if, so I've got 2 vertices, each of them corresponds to a different binary string of length n minus 1, and I join them by an arc if they basically agree on n minus 1 bits, okay? So if last, and I'll give an example here, n minus 1 bits of U agree, so are identical to, with first n minus 1 bits of V. Let me draw an example here. Okay, so for instance, here's U and here's V, and I'm asking whether there's an edge, an arc between them or not. Say U is 1, 1, 0, 0. I don't know why I made this so long. 1, 0. I don't know. So let's make it shorter here. And then V is 1, 0, 0, 1, 0, 1, say. Did I get this right here? So the last bits here agree with the first bits here, right? So these like kind of overlappy here. So what this means is I put an arc like that if they agree, okay? In this way. Why is this important? Well, we'll get to that in a moment, but what it means is that the substring U and the substring V could sort of appear right next to each other in a de Bruijn sequence, right? Keep in mind, if I have a de Bruijn sequence, every single length n binary string appears there. These are actually length n minus 1, so they're not quite what I'm looking for. But the point is that these guys here, like if I found U and the next bit in the de Bruijn sequence was 1, then V would appear right there as well, okay? But again, I'm not quite looking for those, yeah, okay? And then I also want to label the arc UV, and let me make sure this one's easy to mess up here, with last bit of V. So in some sense, the difference between U and V, although there's two options, right? I could pick this bit or I could pick this bit. I pick this bit. Okay, I put that on the edge there, okay? In a sense, that's like what was added to U to get V, although I also removed something, right? Because they're the same length. Okay, so this is my digraph. All right. It does take up a little bit of time, but man, maybe I'll just hand wave the end of the proof, although it's actually easy to see at the end and nice to think about. But I want to draw what this graph actually looks like for n equals 4, because it's like totally cool. Okay, so when n equals 4, then the vertices are all length 3 binary strings, okay? And a particularly nice drawing of this graph looks as follows. And I'll label everything in a moment here. Actually, once we label it, we can fill in the rest on our own, but. Okay, I didn't specify clearly, but this is a multi-digraph. We actually have loops and we have a multi-edge here. And the vertex labelings are, let me put them in like red here. So this is 0, 0, 0. This is 0, 0, 1. So that edge is permissible, right? It makes sense. They agree, and actually that edge would be pointing in that direction as well. This loop, right? It actually is just fine because this loop here says that 0, 0, 0 is adjacent to 0, 0, 0 because those two strings agree with each other on the middle two, and the loop can be oriented in any direction. And what would be the label on this loop here? Yeah, it's 0, right? 0. What's the label in this edge here? It's 1, right? It's the thing that's added there. Okay. Then we get 1, 0, 0, and then this one should point this direction, right? 1, 0, 0 points to there, and I get a 0 there, right? Some of these take a few moments to actually see. That goes up there. We get, this is 0, 1, 0. I actually didn't label that, so I'll have to figure it out. 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1. This one's easy. Again, the loop's direction doesn't matter, and it's a 1. This guy goes to this guy. This should be the direction here, because I can tack, yeah, and there's a 1. These have both directions. Okay, you guys can help me fill in the blanks here. This one goes there and adds a 0, yeah, to the end. Yeah, you can like think of it as shifting slightly. This guy goes here. Whoa, is that right? It's not clear. Which direction is this arc here? So I add a 0 onto the end.
100.
It goes this direction. I don't know. You got to tell me. I'm completely confused now for some reason, but I mean, I hope like the definition's just fine. Eric, I can't quite read it, but oh, you filled it in nicely. I'm never going to be able to read it. I got how many little squares on the screen here? 16 or 15 or whatever. But let me fill in the ones I know here. 1, 0. This is 1. This is 0. Okay, and I'll let you guys fill in the rest anyway. Like I didn't do them all. But this is what the graph looks like. Like this thing is awesome, right? All the 0, 1 strings there are there. It's connected up nicely. It has sort of like an unexpected structure. Like this part in here is really cool that these special strings 0, 1, 0 and 1, 0, 1 actually like can both be appended together. You know, with reverse, you know, opposite directions, opposite bits. It's kind of nice and anything. Anyway, so everything gets filled out. But like we don't actually have to construct this. The definition is clear, right? Take all the 0, 1 strings, add an arc if it satisfies that specific property, or don't add an arc. And the orientation is clear as well, and label it 1 or 0 depending on the sort of last bit there. So it does produce it. That's just what this one looks like. Okay, but we can actually. So okay, so now we want to prove the theorem that. Well, oh no, what am I saying? Proof. I'm in the middle of the proof. I haven't made any like. So we constructed the digraph. How do we use this digraph to do anything here? Okay, so we need to use the fact that this has an Euler tour. So this guy actually has an Euler tour, and it's not perfectly clear that it has an Euler tour or what it means. And this picture is actually helpful to figure it out here. Yeah, so let's make an observation. Each vertex V has, what can you tell me about its in degree and out degree? Forget the picture for just a second, because that actually clouds the issue a little bit. I'll have to clear something up. But if I have a string, let's like, you know, prove it by example here. Then how many things is that vertex V going to send edges to? Yeah, in degree 2 and out degree 2, Ethan points out, because I could have a 1 or a 0 added to the end here and a 1 or a 0 added to the end here. And both of those correspond exactly to other vertices. And those other, you know, this will literally send edges to the other 2 vertices with 1, 0 added to the end of it. And of course, 0 is vanished, and then 1, 0 with 1 vanished. Those are length n minus 1 that do point to it. So out degrees 2, in degrees 2 for every single vertex. Okay, so what's important here actually is that out degree, how did we call this? I think we did OD V equals ID V. They're both 2. Okay, that's true. And if you examine this picture, somewhere like here, it's easy to see. Actually, I didn't label this one, but we now know that that should be out. So these vertices are easy to see that they're in and out. This one's also, I didn't label them all, but you see these 2 arcs are okay. At the loop, things are a little confusing, but how does a loop play into in degree and out degree? Yeah, it contributes 1 to the in degree and 1 to the out degree. And that actually makes this one fine as well. It's out 1, in 1, and then out and in 1 from there as well. Okay, so like maybe we didn't specify that when we defined out in out degree. I don't remember how it was defined exactly, but this certainly is that. Okay, so now we can use the following theorem that says a digraph D has a directed, again, the term directed is redundant because of how we define walk, but directed Euler tour, so closed walk that uses every edge exactly once, if and only if. Before it was if every degree is even. In this case, it's even nicer. It's if and only if for every vertex V, the in degree of V equals the out degree of V. That's the condition. And in some sense, this theorem about Euler tours is even more satisfying than the other one and more clear, right? If you had an Euler tour, you enter a vertex and then you need to exit the vertex. So in and out degrees got to be equal to each other. That's that it's necessary. That it's sufficient, well, that's not hard. The same proof basically works. I won't tell you it because it'll be an exercise. But in some sense, and some books do this, it's actually easier to prove this with the indirected, out-directed version and then just remove orientation to get it for a non-directed graph. Okay, so we're going to use this theorem here. Okay, so our digraph D has an Euler tour, right? Because in degrees and out degrees were all equal. Sorry, they happen to be equal to 2 across the graph, but that's even stronger than what we need. We just need that each vertex has them equal, to each other. They could be different values, but here the graph's really nice, okay? Okay, so I don't have a lot of time here, so maybe I'll explain how we get the thing here and let you guys think about it a little bit on your own, because it's like a cool thought experiment regardless. Okay, so walk along, so take the tour. So start at a vertex and just start walking, okay? On my Euler tour. Every step that I take, record the value on that arc, okay? And keep track of bits on arcs. Traversed. Okay, so like, just as an example here, if I started here and said, okay, I'm gonna go here. I mean, I don't know what my Euler tour looks like. Exactly. Okay, I'm back. Am I back for you guys? I was frozen for a moment there. Okay, all right, good. So we start here, and say my Euler tour says there. Great, record a 0. Then say it says take the loop, record another 0. Now walk here, record a 1. Now say it goes here, record a whatever, right? So I just produce a string there by walking along all these things, okay? So, this forms a binary string of length. What's the length here? It's the number of edges, right? The number of arcs in the graph here. How many arcs does my graph have? Actually, handshaking lemma for directed graphs is simple here, but there's 2 to the n-1 vertices, and each vertex has degree, actually not degree, but say out degree 2. So the out degree for every vertex is 2 times the number of vertices gives me the number of arcs. I don't need to involve in degree, because this nicely, unlike ordinary graphs, counts every arc once. Because they're directed, I only count them once. So the length is 2 to the n. So I created a binary string of length 2 to the n. Okay, so it has a chance to be a De Bruijn sequence, but that doesn't actually say that it's a De Bruijn sequence. Okay, so let me hand wave the last part here. So it produces this long binary string, right? That's long enough. And my claim is this string has all the length n binary strings as contiguous subsequences. Okay, so how do I know that? Well, the idea is the following, and maybe I'll show this by example. So the idea is a length n, a length n string. What is that in my graph? It's not a vertex, right? The vertices are length n-1 strings, but a length n string is a vertex and an arc going out of it, right? It's a length n-1 here plus 1 or 0. Every single length n string appears in my graph of this form. It's a length n-1 and then add on a 1 or a 0 depending on what my string is. They all appear in that form, okay? So that's fine, but how do I actually still show that that thing appears here? Well, say my length, I'm going to do this by example. So say I have 1, 1, 0, 0, 1, 0, 1. And then I say, oh, okay, great. I'm looking at the bit here, the vertex that's 1, 1, 0, 0, 1, 0, and string and arc 1, okay? But look at this. There's an edge incoming to this guy here from a thing that agrees on these guys and has something in front of it. I actually don't care what that thing is. So there's an incoming edge to here with 0. There's 0 and 1 incoming to it, of course, right? And I know that exists with a string that agrees on this part here, right? So it's like question mark and then 1, 1, 0, 0, 1. right? I know that. I don't know what the question mark is. It depends on the Euler tour, but I know that there's an incoming 0 like that, and in my it occurs in my Euler tour as well. Okay, I'm not being totally clear here, but like I can just backtrack in my Euler tour, and the only way that I arrived at this was by walking along bits, these exact bits here. That's the only way to get here, because each previous step had to agree on n-2, and then it agrees on n-3, and then it agrees on n-4, and then it agrees on n-5. It keeps agreeing here, and at each step it means, oh, I took that guy, took that guy, took that guy, took that guy. And so when I arrived here, I actually produced this string here, and then the next step will be this 1 here to get this guy. At some point, I also do walk along the 0 as well, right? But that just produces this string here at a later time. That one gets produced at a later time, okay? So I didn't give you the full details. It may still be not perfectly clear, and you don't have to visualize it this way, but the point is every 0 1 string here appears just because of the way we constructed that they agree with each other on those lists. Think about it, bounce it around in your head for a little while, because like it's totally cool. Let me end with one interesting fact. So we produced a De Bruijn sequence here, right, by following the Euler tour. But we didn't actually say how to find the Euler tour. Moreover, if you examine this example for a little while, you'll see that there's more than one Euler tour in this picture. There's like a few, because like okay, so first of all, we need a kind of Fleury's algorithm, but the point is when you're at a vertex, you usually have a couple choices. Unless there's a bridge, you have basically two choices on average, right, for where you can walk. Like roughly, I mean, it depends on what's happened so far, but each step you have roughly 2 choices. And the point is there's a lot of different Euler tours, and any of those Euler tours will produce a De Bruijn sequence. The proof relies on that thing there. And so the point is there's multiple De Bruijn sequences of order n, of length n, okay? So let me just tell that number then. So the question is, how many De Bruijn sequences of order n of minimal length, right? There's infinitely many De Bruijn sequences of order n, because you can just like add stuff on, but I want those that are of length, minimal length 2 to the n. How many are there? It's cool. There's 2 to the 2 to the n minus n in the exponent. There's that many. Like this is a very unusual number to encounter, double exponential, right? There's this many, and this is exact. This is beyond. I mean, this is actually provable. This is beyond the scope of what we're going to do here. But the number of them, there's this many unique strings. So it's like weird. Like the initial question is, can we even find them? And it seems like hard. And then it's like, not only do they exist, there's a huge amount of them. They're like relative, they're common. But not every 0 1 string of length 2 to the n works, right? You can definitely come up with ones that are not. That's why there's this minus n in the exponent, right? 2 to the 2 to the n would literally be every single way of finding a length 2 to the n string. They can't all work. So there's that many not there.